Hi guys. So tonight we're going to talk about list manipulation. So this is not a deeply mathematical topic, at least at first blush, but some of the things we can do with lists are going to underlie some of the significantly more complicated operations that we can perform if we can do these list operations. And two of the most important ones actually are inspired by mathematics, in particular, mathematical operations that exist in linear algebra. We're going to start by talking about the functions inner and outer, which represent two of the most interesting ways and useful ways that you can combine two lists of data together. And I like to think about these things as vectors because ultimately they're inspired by linear algebra. So there's two different vector products in linear algebra. There's the one that we all know called the dot product, which is the inner product. And then there's another product of vectors called the outer product. And that's actually where the names inner and outer come from. So I'm going to walk you through what an inner product is and then show you how that constructs what the inner function actually does and how it generalizes the dot product from linear algebra. And then we'll talk about the outer product and the outer function afterwards. So the first thing is, when you write a dot product down and you have this v dot w is equal to v1 w1 plus v2 w2 and so on, what you're doing is you're taking two vectors of equal length, so v1 through vn and w1 through wn, and you're mixing the elements of those vectors together by gluing the first and the second and third together with a multiplication, and then you chain all of those together with addition. That's how the inner product is defined. One way of thinking about how that arises is to think about this matrix multiplication, W transpose V. So W transpose V is a row vector, that's W transpose, times a column vector, that's V. And when you do the multiplication, in a standard matrix multiplication, what's happening there is the one row is being multiplied by the one column because you have a 1 by n row times an n by 1 column, and the result is 1 by 1. So this W transpose V vector notation is one way of writing down a vector product, a way of taking two vectors and multiplying them together. So the function inner is a generalization of that same inner product, and we can replicate it using this command. So what inner does is it takes two lists in as its middle entries. So we have ABC and DEF. And then the first entry, the first argument of the inner function is how are you going to combine the elements of the list, of the first list, with the elements of the second list. In this case, I'm going to combine them with multiplication. So in a standard dot product, if I took a dot product of this vector and this one, what I would expect to get out would be A times D, and then B times E, and then C times F, and then I would add them all together. So the times here tells me take the first element of the first list and the first element of the second list and multiply them. Take the second element of the first list and the second element of the second list and multiply them, and so on down the chain. Now, the command over here tells you what to do with that combination of elements once you have them all taken care of. Once you've combined all the elements of the first list with those from the second, using whatever function you put first here, times in our case, how are you going to chain all of those combinations together? So one way of doing that is with the function plus. So what we've written right here is the direct definition in Mathematica of the dot product. It's an inner product where first we multiply elements of the list together, and then once we've got the result, we multiply down the list. Now the beauty of the inner function itself is that I can put any function I want that can combine multiple elements together in the first and last slot of the function. So suppose I wanted to do a version of the dot product of two vectors, but I didn't want to multiply the elements together, I wanted to divide. Well, I can feed the divide function in the first place, and what will happen is it's going to take the entries of the list, but now it's not going to multiply them, it's going to divide them, so it's some kind of reciprocal dot product. And because I have plus right here, what the plus is doing is it's taking all of those elements, A over D and B over E and C over F, and then combining them together with addition just like before. The last thing that we see here the last example we see here is one where we've put list in both slots. And it's worth taking a moment to think about what that does. So if we're listing things, we're taking the first element A of the first list and the first element D of the second list, and we're combining them, but now inside of a list. And that's what this entry AD is. That's the result of combining A and D, not with a multiplication, but with a list object. And then the list over here, when we're all finished, what that's doing is it's saying, okay, now take all of those objects and wrap them up in a big list of coordinate pairs. Okay. So inner is a very useful way of boiling two lists of equal length down into some combination of the elements of those lists where we go one by one. First and first, second and second, third and third, fourth and fourth, fifth and fifth, and so on. So there's another product that we can think about when maybe I don't just want first and first. Maybe I want the first element to be combined with all of the elements in the second list. And I want the second element in the first list to be combined with all of the elements in the second list. And that's going to be what the outer function does. So the outer function, the outer product in linear algebra is what you get when you take, instead of W transpose V, which takes a 1 by n times an n by 1 and gives you a 1 by 1, instead you flip the order of the matrix multiplication. So now we're doing a column vector times a row vector. And column times row is going to be n by 1 times 1 by n, which is an n by n matrix. And so we're going to get an n by n matrix of entries. And that's what the outer product actually does. So I'm going to demonstrate the outer product first. So I've defined here two vectors, v and w. If I like, I can show you what v and w are. So v in matrix form. So there's v in matrix form, and here's w in matrix form. And you can see that I have a column vector and a row vector. Now, if I take those two things and I dot them, what I'm going to get out is this list of combinations where if I show that in matrix form, you can see that it's the matrix that combines every single entry of the first list with every single entry of the second list. So the outer product doesn't take the two vectors and combine them up into a single thing like the dot product does. The outer product produces an array, an n by n array of combinations of all of the elements of the first list with all of the elements of the second. And here we only have one operation, which is multiplication. And the arrangement in the matrix is sort of what the second operation is. And we're going to talk about a way to undo that if we want to. So in the function outer, we can do what we just did, which is to say that we can take two vectors and multiply them to get an array combining all of their entries by performing this computation. So if I take ABC and DEF as two lists, and I take their outer product with respect to the times function, then that's the classic linear algebra outer product. That's the same computation that we did right here. But just like with the inner function, sometimes I might want to have all possible combinations of the first and the second that don't have a multiplication. Maybe I'd like to use divide. Well, I can do that. I'm putting it in matrix form here because I'm trying to emphasize that the output is a list of lists. If you take the matrix form off, you get the standard list of lists type array structure. And I'm using matrix form to really emphasize the fact that this is an n by n array that comes out if you put two n length lists in. So to show you some of the things you can do with it, maybe we're trying to compute binomial coefficients off these two lists. Well, outer is perfectly happy to take binomial as the function it uses to combine elements of the first list and elements of the second. Finally, I guess I should talk about what happens in the outer case where we have lists. Well, if I want all the possible pairings of entries from the first and entries from the second, I can use outer, but now I can apply the list command to do that. And I mean, there's more than one way to do this, but this is the way to do it with outer. So I've made all of the sort of pairs, right, of elements consisting of elements from the first list and elements from the second list. And this structure is actually kind of complicated because now we've got a list, which is the matrix, with lists inside of it, which are the rows, which have lists embedded in those. And you can see that more clearly if I put this in matrix form. you can see that what we're looking at here is a matrix of lists, which are the rows which have lists inside of them. And it's interpreting all of these as matrices. So that's why we have this weird looking thing, which is a matrix with matrices inside of it. But that's the basic idea. Okay, so another operation that comes from linear algebra that we might want to talk about is the transpose of a matrix. So in linear algebra, the transpose of a matrix just switches the rows for the columns. So if you have the matrix 1, 2, 3, 4, 5, 6, like this one, and then you take its transpose, and let me show you how to enter transpose here. So if you compute the transpose of this matrix, you get the transpose. Now it's not obvious that this is a transpose, so let me put it in matrix form. And you can see that what's happened here is the first row of this matrix has become the first column of this one, and the second row has become the second column. So let's actually look and see what this does on the level of lists. So it's a little bit different when you look at it in list form, but the same operation is taking place. It's switching the first column for the first row. That is, it takes the first entry of each of these two lists and makes it a list out of those. Then it takes the second entries and makes a list out of those. Then it takes a third entry and makes a list out of those. So transpose is an operation that's used to switch rows for columns, and that can be very useful when you're trying to sort of sort two lists together in an interesting way, or a useful way. So that means that we've got the linear algebra inspired operations. So the linear algebra inspired operations are going to be inner, outer, and transpose are the linear algebra inspired functions. Okay, so they're generalizations of the same operations that we're already familiar with from manipulating matrices. Because we're dealing with lists of lists, one of the nice things to be able to do would be to strip out that sublist behavior. So for example, if I'm looking at something like A, B, C, D, E, F, and I want to put the plus, I say I want to switch the plus head onto it. So if I try to do plus at A, B, C, of course, that's just a standard head switch. It will happily do that. It takes the list, replaces it with plus. But look what happens if we do this for something like plus. If we compute the plus at a list of lists. Well, now it doesn't do anything, because what's happened is it's thinking of the list that's inside as the object that it's trying to add to something else. So a head change only changes the top level of a list, right? If you look at the structure of this thing, so if you full form ABC, you can see that it's a list. If you full form this object, we get that it's a list with a list inside. And if we try to apply a head change, the only thing we've changed with that plus is this first copy of list. So it's common when you're dealing with something like a list, say, that looks like, maybe we're trying to add this list You've generated a list with two lists inside of it using one of the commands we've already talked about, either probably outer in this case. So you've used outer, and this is the structure that you came up with. And you really like to add all of those elements up or arrange them into a single list. If you try to put plus on this list, what happens is it does the best it can, and it adds element by element down the sublists. Okay? So it's taking the first entry and adding it to the first entry of the second list and so on. But maybe that's not what we want. Maybe what we really want to have is a list where we take all of the entries and we add them all together. So in that case, a thing that we can do is to use the function called flatten. Flatten is a way of stripping out internal structure, and to flatten a rectangular matrix into a row array. That's why it's called the flatten argument. You're taking a matrix and you're vectorizing it. That is, you're squishing it down until it's flat. And you can see that in the result. If you took this and you put it in matrix form, you can see that you've got a matrix. But what comes out after you flatten it is a flat. So what comes out after you flatten it? Well, you just get a squished matrix. So it's representing this as a row, but the idea, so it's representing this as a column, but the idea, it's taken this square matrix and squished it down into a single vector. So flatten is extremely useful at cleaning up lists of lists when you want to act on the entries that you've created, but you don't care about the structure that's been created, say in like the outer function. So it's very common when you're doing using the outer command to blend two lists together so you get every possible combination, to have to flatten the result into just a regular old single list. Other operations that might come up once you have a single list are things that act on the elements of that list, right? In this case, you could think about it as an array, if you like, or related to an array. So we've already seen the command most, and what most does is it throws away the last entry of a list. So if we computed the range of 10, and then we applied the most command to that, then it throws away the 10 at the end. Now, maybe we don't just want one element gone. Maybe we know that regularly we're going to have to drop 2 or 3 elements. We can do that using the drop command. So drop is a way of specifying precisely which elements we want to get rid of. So if we use -1, remember -1 is the index that always means go backwards 1 from the starting position. So the -1 index of anything is the end of it when you're dealing in mathematical lists. So if we drop the -1 entry, we drop the 10 again from the range. If we drop 2 of the entries, so that's what the -2 goes right here, that means start at the end and drop 2. If we dropped 4 of them, we can drop even more of the list. So -4 says drop 4 entries, but drop the 4 at the end. Drop command also extends the rest function. So remember, what rest does to a range is it drops, or what rest does to a list is it drops the first entry. And drop, if you drop 1, and not -1 now, but 1, says start at entry 1 and drop it. And if you drop 2 elements, that says drop the first 2 elements of a list. And then you can drop more, right? Put any number in there, it's going to drop everything from 1 to wherever you end. And if you put negative numbers in, it starts at the end and goes the other direction. The nice thing about drop is you can be much more specific. All right, so what does this do? So this command generates the numbers from 1 to 10, and then it drops entries, and somehow we've only left the first entry behind, because what this specifies is a range of elements that we want to get rid of, starting at the second entry in the list and going all the way to the end. So you can look up the drop function if you like. It's very useful for dropping various pieces of an array, especially when we know maybe that we've got 2 or 3 or 4 or a consistent number of terms that we want to toss off, or we're just interested in some small section of a list that we've produced. So finally, we'll talk about spanning. So spanning, if you've used MATLAB before, is equivalent to the colon command in MATLAB or Python, where you look at all the numbers, say between 2 and 10 is given by 2:10. In Mathematica, the spanning structure is built by using 2 semicolons. So we can use that to call very specific pieces of arrays. So we'll start with range 10. And if I do range 10, of course I get the list from 1 to 10. What this right here means is all of the entries of the array starting at element 2 and ending at element 5. Okay, so what gets selected out is the second entry through the 5th entry, and that's why we get this particular sublist. Maybe I want the elements that start at the 4th entry and go all the way to the end, and that will allow us to call those elements instead, starting at 4th, ending at the end. So spanning is very useful when you're looping, and especially if the looping structure has to change as the step in the algorithm that you're building has to change. This works equally well on symbolic objects. So here's a table of powers of x starting at 1 and ending at 20. When you're using spanning structures, you can introduce a skip size, which means by how many are you going to jump the index every time you move. So this says, starting with a table of entries that begins at x to the first and ends at x to the 20th, start at entry 1, go all the way to the end, and keep every other entry. So first, third, fifth, seventh, and so on. And you can see that reflected in the powers of the list. If you wanted to go by 4s, you would get a different list because now we're skipping by every 4. First, fifth, ninth, and so on. Equally happy to take a different starting entry. So the ability to work with spans inside of lists means that you can always extend or narrow the part of a list that you are trying to work with. One common way to work with this would be something like if you have a list where you're trying to add or multiply elements of that list, but you want to do more each time you go, then say you just had the list pre-existing, it was only computed once. You don't have to recompute it every time you run a loop. You can just recompute the piece of it that you're trying to add up or take the product of as the algorithm that you've designed takes place. So these are some of the basic operations that get used when you're dealing with lists. This is kind of a dry topic of conversation, but it's a really important one because especially when we're dealing with mathematical questions, the combination of elements that we've sorted out algorithmically and then recombining them into new objects is sort of the core of what mathematical programming is all about. And so facility with manipulating lists is a really important skill to develop. So I encourage you, when possible, to use some of the more advanced techniques to combine your vectors of information together so that you get practice working with these kind of structures instead of, especially when we get loops, it's preferred mathematical programming practice to work with the more complicated ways of combining lists together as opposed to constructing them using, say, a do or a while or a for loop. And we will get those eventually. But there's a reason that we're holding off on that, which is to encourage you strongly to build your code in this type of approach. All right, so I'll see you guys later. Make sure you ask me questions if you got them, all right? Take care.